So in the other two videos, we talked about translating, so sliding, and dilating, which is stretching. And we talked about how we can do that vertically or we can do that horizontally. And then the last thing we're going to talk about is reflecting. And so this is a nice little table that you can make to add to your notes. That we have vertical movements and we have horizontal movements. And we have translations where we're sliding things, dilations where we're stretching things, and then reflections. And we're going to add to the reflections um, in this video. So we talked about how translations vertically mean you're adding or subtracting a number on the outside. Dilations vertically mean you're multiplying by a number on the outside. And translations horizontally mean you're adding or subtracting on the inside of the function in sort of the backwards way of what you might expect. Dilations horizontally mean you're multiplying by a number on the inside of the parentheses. Again, sort of backwards of what you might expect. So what I want to do is take a parent function, make it something funky, x squared minus sine of x plus e to the x. Even looking that funky, I thought it'd look cooler than that. Let's do sine to the third. Nah, that doesn't work. Let's do e to x squared. Whatever, we're going to deal with this. Let's make it... interesting. Oh, e to the x squared is not going to do what I want. E to the 7x. Okay, there we go. It's a little lopsided. That's what I wanted. So that's my parent function for what it's worth. I could have done it with any of the parent functions, but I was being picky. So what I want to remind you of is if I make my new function something like 5f of x, I made it 5 times taller, 5 times further away from the x-axis. If I make it 2f of x, it's 2 times as far away from the x-axis. 1f of x is the original graph. 0.5 f of x is closer to the x-axis. 0.1 f of x is even closer to the x-axis. In fact, 0 f of x is the x-axis. But what if I wanted it to go down below the x-axis? As I made that number in front of f of x smaller, my graph got lower and lower and lower and lower and lower. And you probably can conjecture that a negative value is going to actually flip it all the way over the x-axis. If I do a negative 5, I'm doing both a reflection and a dilation. If I do a negative 0.5, I'm doing a reflection and a dilation. The 0.5 part pulls it closer to the x-axis, while the negative flips it over. But here we're just focused purely on the reflecting. And so the point that I'm trying to make, in somewhat of a roundabout way, is that a reflection is just a negative symbol in front of the original function. I hope you can make a conjecture for what it would take to reflect it over the y-axis. Every time we've done a horizontal movement, and reflecting over the y-axis is horizontal, reflecting over the x-axis is vertical. Every time we've done a horizontal movement, we have done something inside the parentheses. So I'm just going to put this negative symbol inside the parentheses, and you can see that the red graph has now mirrored onto the other side of the y-axis. And I know the y-axis describes your vertical location. Like the y value is your vertical location. I understand that. But if you move something as a reflection, notice my hand is not moving vertically. My hand is moving horizontally. And that means that the line of symmetry is a vertical line, but the movement of my shape is a horizontal reflection. So I know that can get a little tricky with the terminology there. So we can take the negative, put it inside, and then these are the different types of function transformations that we are doing. I want you to think about why we don't study a rotation of a function. Maybe you could comment with your answer if you have one. So anyway, there you go. Let me know if you have any questions, and I'm happy to explain.